This video is sponsored by Squarespace. Create a beautiful website without having to write a single line of code. Hello and welcome to Launchpad. I'm Christian Reddy. Today we're going to continue our conversation with Dr. Heidi B. Hammel. In part one of our conversation, we talked about Webb's new observations of the planet Neptune. And today we continue to talk about Webb's observations of the planet Jupiter, what those weird atmospheric features are, and why Jupiter appears the way it does in the near infrared. We also learn about Webb's observations of Mars and talk about Heidi's upcoming programs to further study Jupiter's moons, Saturn, Uranus, and even Pluto. So I give you part two of our conversation with Dr. Heidi Hammel. So Heidi, you are known as the Queen of the Outer Planets. It's a title that I think is so well deserved because you've been studying the outer planets really, I think, just about all your professional career. How excited must you be about eventually seeing images of Uranus? I know you mentioned that earlier, and that is part of your program. So do you know when Webb might be able to see Uranus?
Yeah, we have certain windows that we can look at certain planets. It just has to do with the geometry of how the James Webb Space Telescope observes. It can't look directly out away from the sun and it can't look back. And so there's like this circle that it can observe in, a torus, if you will. And you have to have your object well situated in that window. And our Uranus window is not opened yet. So we're waiting for that to come. I'm looking forward to it. And as soon as we get the data, I will be one of the first people to put it out there and tweet it because I'm sure it's going to be really great. For Uranus, we're going to be focusing a lot on the spectroscopy. That's really where the real meat, the scientific information is. But we will also have mid-infrared images of Uranus, and its rings will be there as well. So it's really the right size to be doing with JWST.
By size, you mean because it's closer than Neptune, so it will fill up more of the camera's field of view?
That's exactly right. It's the planet is about twice the size of Neptune's planet. And the ring system also is about twice as large as Neptune's ring system. So there'll be even more resolution elements. So the pictures will be, even better than Neptune's. And we know it has a really beautiful ring system. We've imaged the rings in near infrared with the Keck and with the Hubble Space Telescope. But based on what we have seen from the Neptune rings, Webb is going to create some really gorgeous Uranus rings images, I'm sure. And wow. So that's going to be great. And of course, the science that comes from them is going to be great too. Really looking forward to that. Well, I would imagine that not only would you be able to study the planet of the rings, but we were talking earlier about Triton, and there are other moons present in the Neptune image. So does your science program also include studies of the moons? Yeah, it in fact does, because the moons that are visible in your images, particularly if you're using one of the kinds of instruments called an integral field unit, an IFU, what those instruments allow you to do is create pictures, but then for each element in the picture, you can pull out the spectral information. And so if you detect a moon, not only do you get a picture of it, which is not going to be exciting because it's not going to be anything except a point, but you will be able to pull out its spectrum. And that will allow you to study the surface chemistry of the moons. And that's what's really going to be interesting. We'll be able to do surface chemistry looking in the mid-infrared, where there's a lot of interesting molecular transitions to give us insight into the chemistry of these moons' surfaces. So that it's going to be a really important and valuable contribution to understanding the Uranus moon system. Wow, fantastic. So can't wait for Uranus. But Webb has also taken a look at one other outer planet, the biggest of them all, of course, is Jupiter. That must have been a thrill to see as well, right? Yeah, Jupiter was just absolutely gorgeous. And I've looked at Jupiter a lot, taken a lot of pictures of Jupiter with the Hubble Space Telescope and other telescopes. And so, you think you've seen it all, right? You think, it's just another picture of Jupiter. But in fact, Webb's near-infrared wavelengths and Webb's really exquisite sensitivity revealed things that we didn't expect on Jupiter. Just two examples is even in the very first images of Jupiter that were taken as engineering data on Webb, just to test how much the bright scattered light of Jupiter, this incredibly bright planet, would mess up the pointing and tracking to see if it would. They took some real short exposures of Jupiter, 75 seconds worth. And in those images on the limb of the planet, which was kind of in darkness just because of the geometry of where the sun was shining, there was a bright layer, a haze layer all along the dark limb. And I remember when we first saw this, people were like, "Oh, your telescope's out of focus." And we're like, "No, it's not. Webb is not out of focus." And so what is that? And science occurred. And people started debating, what could it be? Is it a detached haze layer? Is it ionospheric emission that somehow is, migrating from the polar regions down to the side? But it's just like an echo of the limb. What the heck? That was new. That was unexpected. The great red spot being bright like that, a lot of people are like, "Oh, it must be hot." I'm like, no, this is not a thermal infrared image. This is a near infrared image. So what you're seeing there is scattered sunlight from a high altitude haze layer around at the top of the great red spot. And we knew that, and we had seen that before from some other ground-based images. But that detached haze layer, that was new. And the other new thing that surprised a lot of us was in the polar regions, both the North and the South Pole. Probably not this image. This is some of the shorter wavelengths. We need to have one of the other images, like the color composite that we created with Judy Schmidt. She did a really good job of enhancing some of the colors so that in the polar regions, we could actually see auroral emission in the infrared. And I want to stress that because we have seen beautiful auroral images of Jupiter in the past, but those have been at ultraviolet wavelengths with the Hubble Space Telescope. And so there are transitions in the aurorae in H3+, it's a specific ion of hydrogen that emits in the infrared. And so if you zoom in on one of those poles, you notice that there are little red stripes on that greenish haze.
Yeah.
That's aurorae. Those are the aurorae that we had only ever seen before in the ultraviolet.
Right, with the Hubble Space Telescope, right?
Exactly. But here we're seeing them in the infrared in this H3+ emission. And that, so we kind of expected that. What we didn't expect was that red glow that extends way above the cloud tops of the planet. That extended auroral emission was new with the James Webb Space Telescope. And so that was a fun and interesting result that we pulled out. And you can see it down in the southern hemisphere as well. You can see how that red auroral glow extends thousands of kilometers above the main cloud tops of Jupiter. So that'll be a very interesting new aspect of our models of auroral activity on Jupiter that came from James Webb Space Telescope. That greenish glow that you see in the sort of the upper latitudes, both in the south and the north, that is real. That is a haze. That it looks green because the particular wavelength of light that is most sensitive to this haze was put into the green channel in this color composite. But that is a real haze phenomenon, a haze material encircling the polar regions of the planet. Wow. And the other thing, right in that image that you see, there's these little bright snaky-like things, like the little things. Those are very high altitude clouds that are scattering light back to us before it can be absorbed by the little bits of methane in Jupiter's atmosphere. And so you're kind of looking at the tops of thunderclouds, if you will, very high condensed clouds that are then sort of spreading out in the atmosphere. So there's a lot of rich atmospheric dynamics in an image like this. And here you can see more of them, a sort of streaks of little cumulus cloud tops across that particular latitude. So very, very interesting dynamics that, we do have a spacecraft in orbit around Jupiter right now, the Juno spacecraft.
Right.
So, but it doesn't have this wide field that we get with the James Webb Space Telescope. So using the telescope in coordination with Juno is going to be a really interesting project. There's just a lot of great science.
Hello, my friend. We're going to continue our conversation with Heidi in just a moment. But first, I'd like to thank Squarespace for sponsoring today's video. Squarespace is designed to give you everything you need to create a beautiful website without having to write a single line of code. To get started, simply choose from one of the many mobile responsive templates and use their suite of built-in tools to upload your content. I'm building a new website for our annual workshop for writers, and it's amazing just how easy and intuitive it is. With its new fluid engine, I can move and resize elements and know that they're always going to line up with the overall layout of the site. You can add any type of content, whether it's photos, videos, newsletter signups, e-commerce, or virtually anything else you can imagine. Connect your social media accounts to display posts from your social profiles right on your website. Setting up an email list is a breeze. You start with a template, apply your brand assets, and you're on your way. Even better, the responsive designs will look beautiful on everything from the largest monitors to the smallest phones. If you want to check it out for yourself, just head over to squarespace.com/launchpadastronomy for a free trial and save 10% off your first purchase of a website or domain. You'll find that link in the description below.
So let's talk about Mars.
Sure.
We have a context image from one of the maps just to show you the fields of view. The big white square is a longer wavelength of light. It's a thermal image at 4.3 microns. It's sort of a transition from reflected light to thermal emission. And so the really bright yellow area is really the warmest part of the planet, fading out to the purple, which is cooler because it's not the subsolar point. But there is a structure there, the Hellas Basin, that is different. And, the first thought someone might have is, well, it must be colder because it's darker. And that is actually not correct. It's not darker because it's colder. It's darker because at this wavelength of light, 4.3 microns, there is a carbon dioxide band. And that band, that carbon dioxide emission is very sensitive to the pressure of the atmosphere. And Mars has a moderately thick atmosphere, not as thick as Earth, but thick enough. And so that Hellas Basin is actually a depression on the surface. And so there's a thicker amount of atmosphere over the Hellas Basin.
The atmosphere is deeper, you might say, right? Because there's more atmosphere extending down to get into Hellas Basin. So you're looking through more carbon dioxide. Is that what you're saying?
Yeah. And also the shape of the carbon dioxide is the band itself, the shape of the absorption band in the spectrum changes shape because of the higher pressure at the deeper levels. Wow. And so it's a kind of a weird mixture of an atmospheric effect on the spectrum and what looks like thermal emission. And so you can't take a picture like this at face value. You have to think really carefully about what you're seeing. And Mars is really hard because it's really bright. And we had to be super, super careful about what wavelengths we chose, how short you kept the exposures. There are specialized tools we use to do super fast readouts by looking at smaller pieces of the array, which is why that upper image, which is a sort of a closer in, it's a smaller field of view because we're reading out smaller parts of the detector faster so that we don't overexpose the camera.
Oh, okay. Oh, wow. So you're not even reading out the entire detector. You're just, okay, this is the part of the CCD that happens to be right over Sirius Major. Read that out only.
As fast as you can.
As fast as you can before you saturate, before you blow up. Right. Wow.
Sub-array readouts. It's just a piece of the array. But even in that sub-array readout, like you said, you can see Sirius Major. You can see that Hellas, the Huygens crater, and you can see the Hellas Basin. And the colors are different than they are in the thermal because the smaller inset is at a shorter wavelength of light. And this is reflected sunlight now.
Mm-hmm.
And so there are dark patches and bright patches on the surface of Mars. And that's what we're seeing in that shorter 2.1 micron image. So, pulling together the scientific stories out of these data is not trivial. You don't just take a picture and then immediately understand it. You have to think about it. When you see things like Hellas Basin being dark at 4.3 microns, you have to sort of put your thinking cap on and do science. And Geronimo Villanueva, the person who's in charge of this part of my guaranteed time, is fabulous at this. He even was able to pull out a spectrum that was very hard because most of the spectral regions were saturated because Mars is so bright. But he was a master and was able to pick out enough pieces that were not saturated to put together a full spectrum of sort of representative of kind of a disk average of Mars. And we can see different chemistry in this spectrum. This is just a preliminary one where we can see carbon dioxide, we can see water. We will be doing more detailed analyses of the spectra. One of the questions we hope to explore is this question of the methane mystery on Mars. There are some people report seeing methane, some instruments report methane, others do not. And so why is that? Is it spatially localized? Is it time variable? Is it a combination of both of those? We hope that we are going to be able to add some meaningful information to that dialogue of the methane on Mars by doing some really detailed spectroscopy all around the planet and see if we can pull out something that maybe hasn't been found before.
That would be so amazing. And I know a lot of interest in methane. That is one of the hypothesized biomarkers. So it could indicate, if not life on Mars today, perhaps previous life. Who knows?
Who knows? Or it could, if it doesn't, it could tell us that the methane is coming from volcanic activity or from, slumping on a crater wall that then reveals methane pockets. We don't really know. So that's why it's such an interesting question.
I know this is all about Webb because it's all new and it's revealing so much to us, but the fact that it is new and the fact that it is revealing so many things to us that we otherwise really didn't have the capability of doing before, at least not at this level of detail. What an exciting time to be exploring the solar system.
Yeah, and there's so much more to come. I mean, this is just the beginning. We're going to have comet observations, Kuiper belt observations, studies of Pluto and its spectra, Sedna. I mean, these are all really interesting solar system objects, and all of them are all part of the first year of observations. So, just hang on. There's more.
And I assume Saturn is in there as well.
Yeah,
right?
Saturn's in there. There's some Saturn rings, some small Saturn moons. The program is really kind of looking at a solar system sampler just to give an understanding of what capabilities we can do with James Webb Space Telescope. Can we look at bright things? Yes. Can we look at really faint things? Yes. Can we look at fast moving things? The answer to that is yes. That's one reason I used my guaranteed time for it, because if you wrote a proposal and you said, well, I don't really know if we're going to see anything, maybe we will, that would never get accepted. But because of my role with the telescope over the past 20 years, I did have a large amount of absolutely guaranteed time. Nobody can tell me no, as long as I'm not hurting the telescope. And so I use it for things like this that are risky, that, we might see something, we might not. But if we do, it'll be really interesting. So let's do it. Another risky thing that we're going to try is we're going to try to look for water plumes from Jupiter's moon Europa and Saturn's moon Enceladus.
Wow.
know that Saturn's moon Enceladus has plumes. The Cassini spacecraft saw them for sure. And there is a hint that Jupiter's moon Europa may have plumes. There's Hubble observations in the ultraviolet that suggest the presence of oxygen and hydrogen that might be indicative of water plumes, but might not. And so again, this is risky in the sense that we will look with James Webb Space Telescope, but we may not be successful scientifically. But I think that the risk is worth it. And so that's why, Geronimo and his team are going to be imaging those to see if we can see those plumes. And if we do, we'll be getting spectroscopy and seeing what is the chemistry of the water of those plumes. Could be great. Enceladus will be hard. Saturn's far away. Enceladus is a small moon.
Sure.
Yeah. So it will be hard. That's going to be tricky. And Europa is a gamble. I mean, we don't know. We don't know.
That's why we have people like you who are willing to put up the time and say, hey, I may get nothing from this, but I'm happy to roll the dice. This is what we built Webb for.
Exactly right. So roll the dice.
One of the reasons we built Webb. I mean, so one of the many reasons.
We built Webb. We built Webb to see the faintest galaxies in the universe.
Right.
But the tool that we needed to do that, to see those first galaxies that ever emerged, it's the same tool that we use to look for the water plumes on Saturn's moon Enceladus. Right? If we don't have a spacecraft there, and we don't, right, and not anymore, there's no more Cassini, this is the tool that we can use to study that.
Wonderful. Well, Heidi, I'm so excited. Obviously, everyone's excited about Webb, but it's just wonderful to be able to see how it is letting us learn so much about everything from the very distant universe all the way ahead to the stuff that's right in our cosmic front yard. And I'm really glad that you're willing to talk with us a little bit about it. So thank you so much.
I'm happy to talk. Thanks for giving me the opportunity to share some of this great science.